Hello and welcome to Coffee and Control, the podcast where I find fascinating people from within the world of control and convince them to answer all of my questions. I'm your host, Lucy Hodgins, and my guest today is an assistant professor at Politecnico di Torino in Italy. So I've been wanting to make an episode on game theory for a little while, and I was doing a bit of background research on who to talk to about this topic when I came across this month's guest. So she did her PhD looking at particular applications of game theory and has done a bunch of interesting theoretical work since then. We agreed to meet up at the Conference of Decision and Control and had a wonderful conversation about her research. I would say this episode is a nice mix of theory and application and hopefully accessible even if you don't have a background in game theory. So, get ready to hear about all different aspects of game theory, including resource allocation problems, congestion games, links to variational inequalities, forwards-backwards algorithms, generative adversarial networks, and a lot more besides with my guest this month, Dr Barbara Franci.
I'm Barbara Franci. I'm assistant professor in Politecnico di Torino, and I worked on game theory as a general topic, mostly from the optimization point of view, trying to find a Nash equilibrium under some constraints or things like that.
So you already said you did your PhD on the application of game theory. You applied it to a number of different problems. So I guess the first general question is how did your PhD come about?
I don't know. I did thesis actually in algebraic geometry, so something entirely different. But then I liked the process of doing research. So I decided to go for a PhD because I wanted to explore this possibility essentially. And I did some application around based also on some suggestion from my professor, even if it was for a different topic. And then the opportunity in Turin happened. And the topic was basically on a project that was based on game theory, graph theory, networks problem, things like that.
So I want to start with a kind of basic overview of game theory. So firstly, what defines a game?
To me, a game is essentially an optimization problem. So you want to minimize some cost. But the key aspect of game is just what you do, what the agents do, the players do. It depends also on what the others are doing. So you're trying to minimize your cost, but there might be some variations on what you want to do because other people are also participating in the game, which is essentially as you would do for a normal game, like playing cards or something. It still depends on what the others are doing. Then, of course, there are different levels of interaction with the other players, of course.
So Barbara mentioned solving an optimization to minimize a cost, but equivalently, this optimization can be framed in terms of maximizing what's known as a reward functional. And we're going to come back to this a little later on. So you mentioned in your kind of introduction about the concept of a Nash equilibrium. So what is a Nash equilibrium?
A Nash equilibrium is a situation in which the agents are all minimizing their own cost. They might be different, of course, given what the others are doing. So it's a situation in which, even if in principle there could be a situation in which the cost of one player alone is lower, still, given what the others are doing, that's the best option because going to that other strategy would actually make the situation worse, so probably increase the cost considering what the others are doing. So in a Nash equilibrium, it's really this minimum for everyone, like a social minimum, but depending on what the others are doing, and that the same rule should apply for all the agents.
I just wanted to add a little bit more detail here on Nash equilibria. So Nash equilibria are the most common type of solution for non-cooperative games, so games where each player optimizes their own objective function. As Barbara has just explained, in a regular Nash equilibrium, it's not possible for any single player to improve their objective function by changing their strategy, given that all other players' strategies are held constant. If they can change their strategy and their objective function stays the same, you have a weak Nash equilibrium. But if any change causes this to get worse, the Nash equilibrium is strict. In contrast, a strong Nash equilibrium is one where no group of players can collectively gain more by cooperatively changing their strategy. Future Lucy here, just to say that since I recorded this episode, Alberto has released an episode of the In Control podcast with Jeff Sharma, and in the second half they talk a lot about all different aspects of game theory and various links to control. This was not planned, but there are a lot of parallels drawn with things we discussed throughout this current episode, so if you're interested in learning more, I would definitely recommend checking it out.
Okay, so moving now on to like the details of your thesis. So your thesis was divided into two parts, and the first part was on cloud storage.
Yeah.
So, why did you focus on cloud storage? What are the challenges that you were trying to address in your work?
Yeah, the project was given essentially because it was in collaboration with a company. And their idea was, back in the days, that using a cloud might create some sort of privacy issues or some problems retrieving your data because you have everything somewhere on a third party, essentially, and that you have to rely on them for your backup, for instance. So they wanted to create something a bit more local. But then, of course, to have something local, you need to have capacity. And the idea was, okay, maybe we can use hard disk or laptops or computer that are more powerful, but at the local level. So if you think of an office in a company, you would have a lot of computers because every employee would have one, and then maybe you can use that network of laptops. So the idea was, okay, how do we do this allocation essentially of the data in a distributed way?
So what are the benefits of applying game theory to these kind of systems? Could you give an overview of like how you can reformulate the problem into a game theoretic system?
Yeah, so in the case, the players would be the laptop or the computers per se, or the person behind computer that has to do this allocation. So it has a bunch of resources available, whatever they are, again, computers or disks or whatever. In a sense, the general idea is, okay, I need to select a good resource to use. The problem is that the other players have access to the same resources. So that's where you have the actual game. You have multiple players and this interconnection with the others. And this, in the most simple case, creates at least a congestion game. So a problem in which the resources might get congested, then how do you do the allocation if there is no storage for the allocation?
So Barbara mentioned congestion games here, and I wanted to put this in the context of game theory more broadly. So in a congestion game, players choose from a finite set of alternatives, and the outcome depends on the number of players that choose that alternative. Now, congestion games are a subclass of potential games, and these are defined as games for which the incentive of players to alter their strategy can be expressed using a single potential function, as we discuss next.
Okay, so kind of a bit more on the technical side of things. So I noticed you introduced a reward function that defined features that you'd like the solution to possess. So kind of what were the features that you used in your work? How did you decide on these? Are there any others that you think could have been useful to have?
Well, the rationale was, okay, first of all, we want the players to be able to do the allocation. So we build this example in which it would be an allocation term. So something that would really depend on how many data were allocated. Because, of course, if I need to back up my data, I need to be sure that all the data are backed up. But then we put also a congestion term, again, because if I have a very congested resource, that could be problematic also for retrieving data or simply for communication issues or something like that. So maximize the allocation, but at the same time, try to minimize the congestion. And then an extra term that we call something like an aggregation term, depending on how you wanted to allocate your data. So if you prefer to use just one resource, then you would have a strong aggregation term so that your data will stay all together. While if you don't care, or if there are more issues related to storage or whatever, then a smaller aggregation term would make the allocation a bit more distributed across resources. And that was also motivated by, I don't know, if you need to do multiple copies or you want to be able to have different data in different resources because you use it at different time or with different specific or something like that. How we came up with that was talking with the company and thinking, oh, what could be useful for this type of model, essentially. And the congestion was one of the first that we thought about, also because from game theory point of view, congestion games are also very well studied, so it was at least a good starting point.
So the reward functional that Barbara used consists of three components that maximize allocation, minimize congestion, and control aggregation using a user-defined parameter. In Chapter 3, she then extended this basic approach to introduce a parameter defining the reliability of a particular resource, as she now explains.
At some point, we tried to add some sort of reliability parameter so that you can choose a resource also based on how reliable this resource was. So if it's always off, maybe you don't want to use it because it's hard to access, or if you know that many people are using it, again, I could make it more reliable on one side, but again, more congested on the other. So to kind of play a bit with that.
An additional interesting aspect of this problem is that because the system is decentralized, each agent won't know a priori what the reliability is of its neighbors. Barbara therefore introduced an algorithm that allowed users to gradually learn this over time and assign resources strategically based on this information.
We consider a bit also this fact of having multiple copies, so try to have them in really different resources, because otherwise it's a bit pointless to have a copy if you store twice the copy in the same resource.
So the next question is, what constraints are present in the game formulation, and what impact does this have on the approach you take to the problem?
Yeah, so constraints depends. In some cases, you have games without constraints. In some other cases, you have only local constraints, so something that is really related to what the player can do based on their own possibilities. And sometimes you have coupling constraints, so constraints that depends on more than one player, so that also the coupling is not only at the cost level, but also at the constraint level. If there are no constraints, it's no problem, of course. If you have only local constraints, again, usually it's not that problematic because it's the player himself that knows its own constraints, so it's not really a problem. When there are coupling constraints, again, you have this issue that you have to take into account what the others are doing. So for the allocation problem, for instance, we had a bound on the capacity of the resources, which goes a bit together with the congestion term, but that was really a strict bound for the capacity. But then if you have other agents using the same resource, you have to keep that into account. And the problem is that when you have this type of constraints, sometimes you have to be careful when you look for an equilibrium, because constraints need to be satisfied, and it's not always straightforward at what you do without constraints you can do with constraints.
Before we move on to the next question, I wanted to add in a little bit more detail here just to set the scene. So the approach Barbara took during her PhD was to apply evolutionary game theory by using adaptation. So an evolutionary game is one where the strategies taken by individuals change over the course of the game, with this being characterized by the learning dynamics of the game. There are a few potential types of learning dynamics, including imitative dynamics, best response, and pairwise comparison dynamics. Imitative dynamics are characterized by agents switching to the strategy of a randomly sampled opponent, and this leads to the use of a particular strategy changing in a way that's similar to how the population of a particular species changes over time in a biological setting. As its name suggests, when following the best response dynamic, each agent will switch to the strategy with the optimal payoff at each revision time. In contrast, pairwise comparison dynamics involve agents selecting an alternative strategy at random and then comparing it to the current strategy and selecting the one out of those two options that has the greatest payoff.
So could you talk us kind of briefly through the algorithm that you used to solve this problem and why you chose to use this particular?
Yeah, so for the allocation problem, we started with the idea of using just a simple best response. And then indeed, due to the constraints, we arrived at a point in which the best response wouldn't find a full allocation. So something that would still be an equilibrium, but in our case, being able to allocate all the data was a key component of the model. So finding a Nash equilibrium that wasn't full allocation wasn't enough. So we modified it with a noisy best response. So essentially, instead of taking the best resorts, sometimes you pick something else. So introducing a bit of randomicity, not completely random. There was a rule on how to pick it, but still to create a bit of changing in dynamics so that if you end up being stuck in something that is not a full allocation, then something random happens and you have time to go on. And also the possible moves from the agents are not just to allocate, but also to distribute, so to move something from a resource to the other. And this, again, was for these ideas that if you have a congested resource, maybe it's not convenient for you anymore, or simply you need to unlock a situation and exit a problematic equilibrium to go to something else.
So your thesis mentioned selfish agents and kind of strategies to prevent selfish behaviors. So what constitutes a selfish unit in this context, and how is this prevented?
That's part of it of the game itself and this idea of finding the Nash equilibrium, right? Because if you are selfish and you're not taking into account what the others are doing, you still might end in a situation in which that is not convenient for you. I don't know, easy example, you really want to use a specific resource and I don't care for the others, so try to put everything in there. But then maybe you miss one extra unit and then what do? You have to do something else. But then maybe by trying to be selfish, it ended up being counterproductive for you. While if you take the other into account, maybe you spend less. Or And having congested resource, again, is not really advised. So maybe the resource might have a higher price for the usage. But then usually with the game, you tend to avoid this situation because one way or another, you have to take into account what the others are doing.
So I think I'm going to move now to the second part of your thesis, which examined the concept of wisdom of a crowd. So what is meant by the wisdom of a crowd, and how did you end up working on this as part of your PhD?
Yeah, completely different topic. No game theory there, but rather opinion dynamics type of things. And I started working it because I went to Santa Barbara to visit Francesco Bullo, and we came up with this idea. So the idea is it all started with a paper from, I don't know, a century ago, I think, in which this guy, Galton, went to this fair and asked the participant the weight of an ox. So they just kept making suggestions, and then, of course, all the samples that you could take were completely different, from 1 kilo to 1 ton or something. But then the average was very close, like 200 grams away from the actual weight of the ox. And called this the wisdom of crowd because every single individual was completely off, besides a very small amount. But together they actually got the correct answer, which is not surprising seeing it in retrospective. But then the question was, okay, what happens when you make it in a dynamic for some opinion dynamics in which agent communicate and share opinion on something? And then we tried to analyze what happens not only at infinitive or the asymptotic behavior, but also what happens in the transient. And what we found is that indeed, depending on the topology of the graph, you can have wisdom quite soon, or maybe not, or maybe never. And that mostly essentially depends if you have prominent individuals, which are what you expect. So someone that is highly influential. So if you have something like a star graph, very hard to get to the wisdom because the central agent is very prominent. But similar behavior you can have also in bigger networks or more connected networks.
Okay, so I'd like to transition now onto more technical details of game theory and also some of the work you've done since your PhD. So, firstly, I wanted to kind of give some of the, a bit of an overview of the different approaches to solving Nash equilibria to kind of set the context. Mm-hmm. So, I noticed that an important concept throughout your work is that of recasting the problem and solving the variational inequality. So could you give an overview of how this works and the link between the variational inequality and the Nash equilibrium?
Yes, okay. So if you think of the game as an optimization problem and you want to find a minimum, then you can think of a variational inequality as yet another way to find a minimum. So for optimization, the connection is a bit more straightforward. It's basically a generalization of what we do in mathematical analysis 1. You want to find a minimum by looking at the derivative, or when you have multidimensional, you look at the variational inequality, which is defined on the gradient. But same idea, not zero the derivative, but maybe zero of the gradient. And for the game, it's still the same idea, only instead of taking the full gradient, you take the partial gradients of the cost function of the players with respect to their own decision variable. So if you have agent I, you would have the derivative with respect to the decision variable I, and then the remaining variables for the other agents are just, in a sense, parameters that are there. And why do we want to do that? Well, simply because variational inequalities are a bit more general as a concept. So there are more techniques available to find a solution.
So mathematically, the variational inequality problem is defined for some set X and operator F, and the aim is to find the point X star in the set for which f of X star is orthogonal to this set. As Barbara's just mentioned, in the game theory context, this operator is the gradient of the objective function, and the aim is to find the collective strategies for all agents that satisfy this variational inequality problem. Now, if you know much about Lagrange multipliers, then you may be thinking that this seems like a very similar idea, and in fact, the two concepts are very closely related, as we'll touch on later.
And then once you have this connection, whatever works for variational inequalities essentially can work for games. So to find the Nash equilibrium, then you would use an algorithm that finds a solution for the variational inequality, and that would be a Nash equilibrium. Of course, there are results that tells you that the solution of the I is really the Nash equilibrium, and it's proven. And this has also the flexibility of including coupling constraints without having something extremely complicated. Because then, again, as you would do in optimization, you characterize the solution using the Karushka-Tucker conditions, which is essentially conditions that ensure that constraints can be satisfied. And then instead of studying just the primal problem, you study also the dual problem, essentially using the dual variable as an extra decision variable. But then if you can control the dual variable, then you're basically controlling the constraints.
So there are a few key concepts here that I wanted to clarify. So firstly, the context here is slightly different to in Barbara's thesis because we're now dealing with the generalised Nash equilibrium problem formulation, which deals with a more general class of constraints in which the strategy of each player is confined to some set that changes depending on the strategies of other players. The Karushka-Tucker or KKT conditions are a necessary condition for a set of strategies to be a generalised Nash equilibrium. Now, the KKT conditions link very closely to the Lagrangian function associated with the variational inequality. The basics of the Lagrangian is that it's defined as a combination of your objective function and your constraints, with these constraints weighted using a dual variable, lambda. The local optimum of your objective function subject to these constraints then corresponds to the gradient of this Lagrangian being 0. I've left links below that explain this in more detail if you are interested.
So I noticed you've written a number of different papers on forward-backward algorithms. So could you give an overview of what this algorithm entails and why it's used?
Yeah, so essentially forward-backward is a generalization of gradient descent. It's called forward-backward because with the gradient, you move forward in the direction of the gradient, and then you take a projection to be sure that maybe the local constraints are satisfied as well, so that's the backward step. And this was, forward-backward is one of the most studied as gradient descent. But then there are a bunch of variation that you can do, that you can add inertia step or relaxation steps or an extra gradient step. You can play with the anchor point. You can play with the point where you compute the gradient. And you create these variations essentially because the general idea is that you want to always weaken the assumptions. Because forward, backward, plain and simple as it is, it actually works basically only under strong complexity. Not exactly the same for games, but we can say strong complexity, which is nice, but it's a strong assumption. And then to compensate with the strong assumption, if you weaken this assumption, then you have to adjust the trajectory, essentially.
So most of your papers examine algorithms for solving stochastic Nash equilibrium seeking problems. So how does this stochasticity arise in the problem formulation, and what impact does this have on your ability to solve the problem?
The stochasticity comes in the cost function. Basically, we assume that the cost function is affected by some random variable. So my usual example would be if you consider the energy market, you want to use renewable resources like solar panels, wind turbines, and such. But the problem is that you cannot know exactly in advance how much they will produce. So you can see that as a random variable that has some feature, but generally it's a random variable that would affect your cost. The fact is that since you don't know their behavior, you essentially say that you don't know the distribution of the random variable. So if you want to compute the expected cost, you cannot because you don't have the probability. So that's the problematic part of the problem. And then what happens is that you can still find a Nash equilibrium if you have enough information. So you know what happens yesterday, the day before yesterday, so you have some data. And using this data, then instead of computing the exact expected value, you compute an approximation. And if the approximation is good enough, then it's more or less the same as in the deterministic case. From the realistic point of view, it's a bit of a problem because usually what happens is that if you have very few data, we don't know enough. We don't know yet if it's enough to get to the equilibrium. In some cases you can, but you really need to take a very small step size. Well, if I don't have enough data, the approximation, it's not going to be very good. But if I take a very small step size, I'm not going just too far away from the Nash. While if you have a lot of data, and by a lot, it's something that grows as number of iterations squared, basically. At every iteration, you need k squared data, which is not really realistic. And sometimes there are indeed works in which we try to quantify how far we go if we have only a finite amount of data.
So just to summarise what Barbara's outlined, there are two different approaches you can take to stochastic Nash equilibrium problems. The first is the stochastic approximation, in which each agent samples a single realisation of the random variable. And the second is the stochastic average approximation, in which the expected value of the cost function is approximated by the average over a large number of samples.
So, I guess you've kind of mentioned this already, but looking through your work, you've done kind of various modifications and improvements to the forward-backward algorithm, and also written papers on some alternative algorithms to solving the problem. So your early work in this area examined distributed forward-backwards algorithms. So why were previous algorithms not suitable for the distributed case, and how did you modify the algorithm to allow?
Yeah, the distributed part comes from the fact that since you have multiple players, you want them to be able to do the computation themselves, and also without having some external party that helps in the communication. So until not so far ago, basically the idea was you have someone else that would compute a solution for you, while in the distributed case, you imagine that the agents themselves are computing their own costs and trying to retrieve the information. So usually you have an actor for the communications, assuming that the agents can talk with each other. And then what happens is that you need to decouple this coupling between the agents, essentially. So you can keep the decision variables of the others as parameters, but then if you want to compute your equilibrium by knowing only your own parties, means that you don't know the cost function of the other players. So in principle, you cannot predict what they would do. While for more classic games like matrix games or something like that, you basically know everything about everyone. That's not the case. From reality point of view, it's not really meaningful. You cannot assume that you know everything about everyone.
I tried to look into what exactly constitutes a matrix game, but there doesn't seem to be a clear consensus. So some sources define matrix games as a class of games in which individuals play simultaneously and only once, whilst others say that this representation is generally used for static games with complete perfect information. Also, in many cases, the term matrix game is used to specifically refer to two-player zero-sum games in which one player's loss is the other player's gain. Regardless of the precise definition, matrix games take a centralised perspective to gameplay, in contrast to the decentralised approach that Barbara was interested in.
And to do that, there was a work for the deterministic case from Professor Pavel that basically used operator theory to do this decoupling. And once you have that, then you move your problem from the optimization problem to the variational inequality and then to this operator problem. So you're now not looking for a zero of a gradient, you're looking for a zero of an operator, which is a bit more general, still yet another way to find a minimum, very loosely speaking. And what was missing, at least what was my work, was, okay, can I still do this if I have some expected value cost, and what changes? And for the distributed part, actually not a lot, because the intuition is still the same. What changes is that, again, you have this problem which, for computing the cost, that you need the samples.
So I think you mentioned already about kind of assumptions and that you require strong complexity for the forward-backwards algorithm. And a lot of your papers examine various different approaches to weakening these assumptions. So could you give an overview of maybe any other assumptions that are placed on the system and how you're able to relax these?
Yes, so mostly you focus on these, not really on the convexity of the cost, but on the monotonicity of the gradient. But for optimization, if you have a convex function, then you would have a monotone gradient. For games, it's not exactly the same, again, because you're not considering exactly a gradient, but something else. But the intuition is still the same. And in between monotonicity and strong monotonicity, there are 3 or 4 other intermediate steps. Of course, the weakest, the best, because you can apply to more cases. And so far, I think monotonicity is still the weakest. Maybe there is something on pseudo-monotonicity, which is a bit less.
So just to clarify, a monotone function is one whose gradient doesn't change sign. So it's either non-decreasing or non-increasing. And a strictly monotone function has a gradient that's either positive or negative and can't be zero. Broadly speaking, a mu strongly monotone function is one where the gradient is always larger than some positive constant mu. And the adjective restrictive is used when a property holds within the set of fixed points of the function. With regards to pseudo-monotone functions, there's a very subtle difference between these and standard monotone functions that relates to the limits of convergent sequences. Also, in the context of games, these properties refer to a so-called pseudo-gradient vector that's composed of the gradient of each of the cost functions of each agent with respect to that agent's strategy. This makes it slightly different from a standard gradient vector.
But for the stochastic case, I think the majority of the things are still on monotonicity. And then there are also some conditions that you can put on the solution, or maybe try to have this assumption not to be global assumptions, but maybe work only locally around the solution, so that at the beginning weird things can happen, but then when you are close to the solution, then maybe something like local strong convexity around the solution, then once you're near enough, you will converge to the solution. And that depends on the type of iteration that you have, and usually what happens is you start proving something and see what you need to make it work. And also at the same time, you try to compromise also with the computational burden, because one of the reasons why forward, backward, or gradient descent are used is because it's just one step. So computing the gradient might be expensive, but you do it only once per iteration. While something like the extra gradient, you have to do it twice because there is an extra gradient step. So it works under weaker assumptions, but then it might be computationally more challenging. And sometimes you find also estimation of the convergence rate and all these things. So you have usually some classification of these algorithms depending on their performance. And in some cases, if you add like relaxation step or inertia step, you can play a bit with the step sizes to adjust the trajectory. And in some cases, you can have also maybe time varying step sizes, so that when you need it more, you do some tuning. You can add line search, which is really tuning the parameter depending on where you are.
Barbara mentioned using relaxation and inertial steps here, so I wanted to add a little bit more detail. So these are two fairly standard approaches to improving the convergence rate of fixed point algorithms. So the inertial algorithm is closely related to the well-known Nesterov's accelerated gradient method, which modifies the update step so that instead of just following the direction of the gradient, you move slightly in the direction of a so-called velocity term. Relaxation algorithms take a slightly different approach and instead combine the current operator output with the previous iterate, as Barbara now explains.
This might be a little bit technical, but one of your papers looked at extending the relaxed forward-backward operator splitting method to the stochastic case. So how does the relaxed approach differ from the traditional algorithm?
So the relaxed paper, we basically added some kind of linear combination step. So instead of computing the gradient, so usually gradient descent, you compute the next step and then use that as the anchor point for the next step. While in the relaxation step, we moved a bit the anchor point, so that instead of using the previous iteration, we would use a linear combination between the previous iteration and the previous anchor point. And this came from a result from variational inequalities. That was only for deterministic variational inequalities. And the idea first was, okay, can we make it something for games? And then what happens if we have this approximation of the costs to adjust? And the relaxation step doesn't have an effect on the gradient step per se. The same computational burden because you have still just one computational gradient. But with this relaxation step, you can relax also the assumptions. So now you can use only monotonicity, which is better. And then it agrees also with the approximation part, so that if you have enough samples, you can get to the equilibrium. And if you don't have the coupling constraints, actually in the case, you can get to the equilibrium also if you have just one sample at every iteration. I think it's a good compromise because it works in different cases and with relatively weak assumptions.
So we've kind of talked about a lot of different algorithms. I know you've also written some papers on projective reflected gradient and extra gradient methods. So I guess, how do you decide which of these algorithms is best for a particular application?
Well, it depends a bit on what you want to do and what you see that could work from the variational inequality community and how you can modify something. Sometimes it's just intuition, or sometimes it's like, what happens if I add this term? Can I show that it converges? Is it good? Would it go fast enough or something like that? Or in some other cases, it was a bit more on the theory side, again, checking all these properties for the projector effector, for instance. We did a bit of study of what could be the condition that would make it work, and we found that there were more than one. The problem, let's say, it was that you still need a bit more than monotonicity, but there are a number of intermediate, again, conditions, local conditions essentially, and that we show that all of them could be used essentially to get to the equilibrium. So for that, the point of view was more providing options depending on the type of assumptions that you have and saying, hey, this algorithm works with different assumptions, so maybe your problem would have one of these.
Okay, so I guess moving on to more application, I wanted to ask about your work on generative adversarial networks. So what are generative adversarial networks and why are they useful?
GANs are a two neural network. They compete against each other for the training process. And you have a generator and a discriminator. The generator generates, say, images, and the discriminator tries to tell if these images are real or fake. The usual example from Goodfellow, which was the professor who came up with the idea, was, you can have a team of counterfeiters and the police. The counterfeiters are producing fake currency, and the police is trying to detect fake money. Now, since they have this adversarial problem, you can write it as a game. It's a two-player game only, but still, because their behavior depends on what the other are doing. The generator improves by receiving feedback from the discriminator, but the discriminator needs the images to detect them. And it's actually a stochastic game simply because when you have all this data, you have essentially an expected loss. And that's it, essentially. Once you have the game, then anything is the worse for game can in principle work as a training algorithm for GANs.
Yeah, so I guess you've already kind of explained how game theory can be applied to these systems. Why were the algorithms that you developed in particular so well suited to these systems?
Well, the fact is that in most of the machine learning community, until some years ago, but I still see it sometimes now, they use gradient descent all the time. And sometimes you find paper in which the authors are surprised that they can find a counterexample where gradient descent doesn't work. Then you see the theory and say, okay, but gradient descent, you're really sure that it works, only we have strong convexity. Now, in most of cases, machine learning is not even convex. So it's clear, to me, it's clear that you can find counterexample of the algorithm not converging because you don't have the assumptions. While indeed, from my point of view, I could at least provide something that will work under weaker assumption. Not convexity is still a problem, but at least instead of having strong convexity, you can have something weaker, which in principle should be better. And then we tried to see how, I think I used the reluctant forward-backward for the GANs paper. We tried to see how it would perform compared to a couple of other papers. And we took gradient descent, extra gradients, and mine. And at least we showed that it could compete with the literature.
So you've also written some really interesting papers looking at how to find Nash equilibria in cases where the information available to agents is either not complete or is misleading. So I guess the first question is what's the motivation behind this and what kinds of systems could these algorithms be applied to?
Yeah, so the idea is, as I said, the agents need to communicate to know what the others are doing, to compute their own costs, their own constraints, blah, blah, blah. But it's not really realistic to assume that, again, everyone can talk with everyone. So, again, energy market, you have your grid. Maybe you can assume that they can communicate with the neighborhood, but they don't know how to communicate with the other side of the city. Still, what happens in the other side of the city might have an effect on how much they pay in energy bills simply because the energy company is the same all across the city, right? I'm making it simple, but just to get the idea. So what happens is that you try to pair the Nash equilibrium seeking with an opinion dynamics in which the agents can communicate with the neighbor and try to retrieve the missing information by talking with them. So maybe agent 1 can talk with agent 2, but not with agent 3. But if agent 2 can talk with agent 3, then agent 1 can still retrieve information about agent 3 by talking with agent 2. Yeah, so the idea is, can I still find an equilibrium even if I have this missing information, but with the communication? And in general, the answer is yes. Yeah, of course, also there depends a bit on the topology and all these things, but in general, yes.
So I guess starting off with the case where you only have partial information, how does your approach to tackling this kind of systems change where you don't have the full information?
It changes because you have to learn not only the dynamic to get to the equilibrium, but you have to learn also what the others are doing. And these are two learning processes though, that you do in parallel. So sometimes you might have a situation in which your estimation of what the other are doing is not very good. So this slows down a bit the equilibrium process. But at the same time, the fact that you're looking for an equilibrium would also adjust a bit the estimation because then you're communicating what you're doing to the neighborhood. So it changes a bit the dynamic of the game.
I wanted to add a little bit more detail on this work because I find it really interesting. So in the distributed case, A particular collective decision is only a generalised Nash equilibrium of the game if the dual variables associated with the constraints all reach a consensus. And this is the case regardless of whether you have full or partial information. In the case of partial information, each agent progressively updates its estimate about the action of other players that it doesn't have direct access to. So, the basic steps of the algorithm in the case of partial information involves first updating each agent's decision variable, then updating the estimates of all other agents' actions in a way that pushes this towards a consensus, then updating the dual variable, again in a way to push this towards consensus, and then finally using a projection step to ensure that the dual variables are all positive.
So this paper considered both network and aggregative games. So how do these differ and how does this impact your approach?
Yeah, network games are usually the general partial decision information type of problem is simply my cost function is affected by the others. I need those information and I try to retrieve them by communicating in the network. So it's more like a general case. While for the aggregative case, you have the cost function that depends on an aggregative value that depends on what the others are doing or also what you're doing yourself, but in a aggregative quantity. So you might not need to know exactly what the others are doing or estimate the decision variable, but you can look at estimating the aggregative value itself. Still, by communicating with the other, try to estimate what the others are doing. So for how I see it, the aggregative phase is a bit of a particular case of this partial decision information type of games.
You also in this paper discussed node-based versus edge-based algorithms. So what are the kind of advantages or limitations of each of these, and is one more useful in certain situations than the others?
Yes, if I remember, the idea is just a change on how you write the opinion dynamic. If you do it either based on which node can communicate with which other node, or if you look at what edges you can have the opinion flowing, essentially. And from the theoretical point of view, it's not a big difference in the sense that the matrices that describe this node-by-node connection or node-edge connection have usually the general same properties, so it doesn't really affect a lot the theoretical part. But then for the application, you're using slightly different opinion dynamic. It's also sometimes might be also a dimensional problem, because if you consider the edge of the nodes, you have different numbers, of course, communications, but it's just two variants of the same.
Last year, Barbara published a follow-up paper that considered a very interesting variation of this problem, in which the agents had some bias against certain other agents, as she now explains.
Well, the idea is, okay, first you start with the game and you want to know what the others are doing, and you say, okay, we talk with each other. Then you say, no, I don't want to talk with everyone, I talk only with the neighborhood, so you reduce the information. And then the next step is, but what happens if this communication is not good for whatever reason? So you have really a technical problem in the communication, or you have an agent that is trying to say something wrong, or maybe it's just that between all the steps at some point there was noisy, so you're just getting something misleading. It doesn't have to be intentionally bad or wrong or counterintuitive, but it can happen. So you need something to try and avoid this problem. And so far what we did was, instead of trying to know exactly the decision variable, we tried to know what is the most likely one, the most probable one to happen. So you're basically looking for a probability distribution over the possible decision variable. Of course, you have to compromise with what the agents know, because if you need to create a probability distribution over the decision variable of the others, you need to know at least what are the options. I think as a side result, you don't need to know entirely all the options of what the others are doing, but in a sense, you have to guarantee that at least the equilibrium one is in your set.
So in the final technical part of this interview, I asked Barbara about a paper that she wrote on generalised Nash equilibrium problems in cases where the agents are transmitting purposefully misleading information. And before I read this paper, I thought that this might just be a small variation on the biased partial information case. But in fact, this paper made use of a best response dynamics type algorithm instead of the variational inequality approach used in previous papers. And there were a few other modifications made as well.
That came because from the variational point of view, we're still trying to figure out how to include this miscommunication in general. The problem we faced is that since you have Now, thinking of the dynamic, you have this coupling in between the Nash learning and the decision learning. If you have some problems in one of the two branches, then that would affect also the other one. And mathematically, I wasn't able to see how this effect can compromise the result. So I have some ideas, but I don't know if they work, and what I tried so far didn't work. So the other approach came because of considering the problem from a different point of view, and indeed we consider just matrix game and not an optimization problem. But because in that case, we could use some tricks from probability statistics and some Bayesian learning to get to this probability distribution. But then it was also a fact that, in principle, if you can see the game as an optimization problem, you don't necessarily need to have a finite set of strategies. So usually you can say, have an interval. So I don't know, if X is the consumption of energy, it's going to be bigger than 0 and smaller than some upper bound, right? So, but it can be any number in there. While in this case, to have this probability distribution, it was, well, in a sense, easier to do it in the discrete case. So you needed to have a finite number of strategies and just build the probability on that.
Okay, so I noticed the paper you're presenting at CDC is kind of related to this. So could you give an overview of what your paper is about and kind of extensions that you made to previous works?
Yeah, so the idea of this paper is a bit different because, I told you that you want the algorithm to be distributed so the agents do the things themselves. Okay, now instead we go back to having a third party that kind of monitors the problem. We call it an external entity. The application that I'm going to use for the presentation is you have some electric vehicles that need to charge their cars. So the distribution system operators want to be able to predict what they will do. So you have the cars that are essentially playing the game because when they plug in depends also on when the other cars are plugged in, simply because cost of energy or availability of the towers. But the DSO really need to know what happens to fix the prices and make the planning.
Here, DSO stands for Distribution System Operator, and they're the organisation that operates and manages the regional energy distribution network.
And that's the idea. So you have this external entity that is trying to predict what the agents are doing. The communication here goes from the bottom to the top. So basically the electric vehicle can communicate their best response in the sense of Nash equilibrium. And then what the external entity wants to do is learn basically these best response actions without knowing the cost of the players, but knowing only what they're doing, or at least what they communicate. Now, the paper started from a deterministic case that the other two co-authors did, and then they called me for the stochastic part. Because what happens is that, the agents are playing, they're doing the best response, and then communicating the external entity. But what happens, again, if there is some noise, some problem in the communication, so some random variable that compromise what they're communicating? So that basically the external entity receives this noise information about what the players are doing, and using that information tries to learn a map that describes the best response. So basically it's learning some parameters that would give information about this map. And then propose a best response itself and communicate it back to the agents. Well, the agent can use that because in principle, this works also in the case in which the agents cannot really communicate with each other. And then the good news is that the external entity can indeed learn what the agents are doing and is able to predict what would be the Nash equilibrium, even if there is the noise.
Okay, so that's kind of all the technical parts of this interview. I've got some other quick fire questions at the end. So firstly, what's the best piece of advice you've ever received?
That's actually a very difficult question, but I think a lifesaver is that you can say no. I understand that sometimes it's hard, especially if you're like PhD students with a supervisor, you don't really want to say no, but it's also survival, So at some point it's fair to say, no, I cannot. And it's not really going to compromise. I mean, if you always say no, but if you don't want to do it, if you just don't say no, I don't do it.
What's your favorite part of your job?
Well, now that I'm in Rio de Janeiro, I want to say traveling. No, actually, I do like the research part a lot, getting to just study things and see what happens if we change just a tiny bit.
Are there any other areas of kind of control or optimization that you'd like to work in aside from game theory?
I'm now moving actually more toward the machine learning community because there are a bunch of things that we can still do coming from the game theory, but also from control theory for AI in general. You see, the Gantz paper was a first step in that direction. Now I hear that the trend is in diffusion models, which apparently you can write as Markov chains. But then as a mathematician, once you have a Markov chain, you can do a lot of things in there. So maybe something can help in there. More from the control part. Yeah, the fact is that I never really studied control as control theory because I have a degree in pure mathematics. And then my approach to control theory was via game theory when I started coming to these conferences. But I was thinking, also listening to some talks this morning, that maybe introducing something very classic like feedback control together with the game, which I think it exists, but to use it maybe for these communication issues.
So game theory and control theory have very close links, and back in 2017 there was a Control Systems magazine issue dedicated to the role of game theory within control. One particular article that caught my eye and links closely with Barbara's PhD work in particular was titled "The Role of Population Games and Evolutionary Dynamics in Distributed Control Systems, the Advantages of Evolutionary Game Theory." This explains that control problems can be viewed as games by associating control inputs with the available strategies, and the control objective can be framed in terms of the payoff function. This article also highlighted the advantages of applying game theory to these type of distributed systems, in that game theory inherently deals with local information, which naturally leads to a distributed framework when applied to control problems.
Who's your role model within the field of either kind of game theory or applied maths more generally, or pure maths?
Role model, I think sometimes you see people that are inspired when they do their seminars, that they really like what they're doing. I think the fact is that what is important is not how famous you are as a researcher, but it's also how you are in the one-to-one. Because during this career, you work with many people, and what really makes a difference is not how knowledgeable they are, but how they communicate with you. So I think I'm grateful to some of my supervisor, and I hope to be as good as them. Also, I'm also grateful for the bad parts, because then they help me. They show me how I don't want to be, but also what I want to be and who I want to be.
What has been your favourite paper or project to have worked on?
For a paper, I think it has to be the relaxed forward-backward Nash equilibrium seeking, because the first forward-backward one, I felt more like, let's try to extend something that was already there from the deterministic to the stochastic, but I felt a bit more easy to say, while the relaxed one was really a work in which we put a lot of effort and consider a different variation, and it's really a nice paper.
That's all my questions. Thank you so much.
Thank you.
So, in summary, distributed systems like cloud storage are well suited to game theoretic modelling, especially congestion and population games. Variational inequalities provide a powerful framework for analysing and solving Nash equilibria. Solutions of these can be computed using the forwards-backwards algorithm, and variants of this, such as the extra gradient, inertial and relaxed algorithms, allow for trade-off between convergence speed and strength of assumptions. Stochastic generalised Nash equilibria occur in cases where the cost function are dependent on some external random variable, and these are often crucial for modelling real-world scenarios. Generative adversarial networks consist of two neural networks that are pitted against each other, and game theoretic methods give strong theoretical foundations for understanding this learning process. And finally, game theory has strong ties to control, and there are many applications where both disciplines offer valuable insights into outstanding problems. I really hope you've enjoyed this episode. I apologise for the background clicking in Barbara's audio. I am still not quite sure what caused that. I did try and remove the worst of it, but I hope it wasn't too distracting. As always, you can get in touch with me via LinkedIn or follow the podcast on there. I've also created a feedback survey to try and get a feel for the kind of people listening to the podcast and how I can improve it. I've left a link to that below. It would be fabulous if you could fill out all of it or even just some of the questions. Next month's episode is going to be another episode that I recorded at CDC, this time with a researcher from MIT about his work on co-design. We do also touch on game theory a little bit if you're still hankering for some game theory content. That will be released on the 1st of March, but until then I hope you have a wonderful month.